one of the most important concepts in mathematics is the concept of equality. The idea that two numbers or two objects can be equal to each other. Now, if two numbers are not equal to each other, there is still a way to talk about the relationship between them, and that's really what an inequality is. So an inequality is a way of describing a relationship between two numbers, which aren't necessarily equal. So, to put it kind of succinctly, an inequality it's a relationship So it's a relationship between the relative positions of two numbers on a number line. So the relative positions of 2 points on the number line. That's what an inequality is. So let's draw a picture to make this more precise, shall we? So a picture So imagine I've got the number line going off in both directions, as always. And imagine I choose two positions. So let's choose a point here, A, so a number A and a number B. So clearly they're not equal to each other because they're not on top of each other. But there is still an important thing to say about them. So the number B is to the right of the number A, and the number A is to the left of the number B. So this is the real number line. So to express this fact, the fact that they are kind of side by side in a particular orientation, we say the following essentially. So here are two simple ways to say this. Two simple ways to say this. Okay, so what I'm going to say is two kind of mathematical pieces of notation which describe the picture we're seeing here. So one way of describing it is we say that A, and then we do this kind of arrow business, B. So we either write this, or we write it kind of the other way around, or equivalently, we could write B, and then we use kind of the arrow symbol here, but the other way around with an A. So what does this mean? Well, first of all, this should be read as follows. So I'm going to give you two ways of reading this symbol. So this is shorthand for the following. So if I was to say this out loud, it would be A is to the left of B on the number line. A is on the left of B on the number line. Okay. Another way we could say this, which is much more common, would be to say that A is strictly less than B. And when I say strictly less, I am literally meaning what I'm writing here. It's to the left, right? So it's on the left side. So a slightly different way of writing this or saying this, which is much more common, is A is strictly less. Strictly less than B. Now over here, same basic story, except we would describe it from the kind of other way around if you want. So we'd be saying here really B is to the right on the number line of A. So we're only saying like this because B is leading, right? It's the first thing that turns up in the expression. So B is on the right of A on the number line. Okay, A is to the right. So again, we could say this slightly different way. We could say this as B is strictly greater than A. The strictly means it's not equal. So B is strictly greater than A. It's another way to express it. Okay, so let's do some super quick examples to make sure we're completely understanding this idea. So, examples. So let's draw a number line and mark a few points on it, shall we say? So if I was to give us the numbers, let's do -5, -4, let's say. Let's have -1 over here. This isn't to scale, it's a bit of a mess. Let's have 1, and let's have, I don't know, let's have 3 up here. In fact, no, let's do 2 as well. So this isn't the best drawn number line in the world, but that's kind of vaguely correct position. It's a bit of a mess, but it's okay. So from this, I mean, they've got lots of relationships between things. Just as a few examples, we can see immediately. So if I just focus on this piece here. Well, 1 is to the left of 2. So I could write this guy down as... Where am I? Oop. So I could write that as 1 is less than 2. Or you could write 2 is greater than 1. Nothing wrong with that. Other examples, we could have, I don't know, if we do 3 and -1, let's say. So 3 and -1 are these guys. So clearly -1 is to the left of 3. So we could have it written as -1 is strictly less than 3. Or equivalently, 3 is strictly greater than -1. And finally, something to understand is it's the relative position. It's not kind of the size of the number, if you want. So -5 is strictly less than -4. It's something to understand. It's about your position on the number line. Even though -5 has absolute value 5, which is bigger than 4, when we're talking about the inequality relationship between -5 and -4, -5 is strictly less than -4. Or we could write, as I've just said, -4 is strictly greater than -5. So it's about your relative position on the number line. Okay, so a few things to be said beyond this. We can beef the notation up a little bit to include the potential for inequality. So if we want to include the possibility that A is equal to B, then we use the same notation. So for less than or equal, strictly less than or equal, or strictly less than was this. To include the possibility that they're equal to each other, we do a little kind of extra line down there to indicate kind of an equal sign. Or we could have greater than, strictly greater than, but if you want greater than or equal, you would include a little straight line down there. Okay, so a little bit of terminology that we are all incredibly familiar with. The idea of being positive or negative is related to your relative position on the number line to 0. So if I take a number A, and A is to the right of 0, or maybe I'll write it like this. Doesn't really make any difference. So A is to the right of 0 here. We say A is positive. It's the meaning of positive, okay? I might describe it as plus. If A is... So that's not addition, right? That's just a symbol for plus. If, on the other hand, A is to the left of 0, we say A is negative. You might describe it as negative there. And of course the other option is a is equal to 0. And then we just say it's 0. Nothing groundbreaking. So if we want to represent this information on a number line, which is something we're going to do a little bit later on with some procedure, if we draw the number line like this, so 0 is kind of dead in the center if you want. Well, the numbers on this side are negative, the numbers on this side are positive, so that's kind of where this notation is coming from. Something to say, which is a little bit of a tangent, is when we're talking about things like length or distance, we always use positive numbers, right? If I'm talking about the distance between point A and point B, it's always a positive number. It could be 0, but two positions which are not equal to each other, the distance between them has to be strictly positive. So you can't have a negative distance between two things. Same with lengths, right? You can't have a rectangle whose side is -4. So this is just something to say about the kind of the fact that we use positive numbers in a little bit of a different way. So we describe length and distance and area and volume and all of these kind of things, but I'll just stick with this for the moment, with positive numbers. Okay, so let's look at a few properties of these. So an important property of the inequality symbol is something called the transitivity property. So here is an important property. Important. The transitivity property. Kind of sounds fancier than it is really. Here's what it states. If I have A less than B and B less than C, that guarantees that A has to be less than C. The word transitive is for transmit, really. So it's like it's transmitting the relationship between A and C through B. That's one way to think about it. And you could do this with, what's going on? You could do this with less than or equal as well. It's all exactly the same. Or greater than or equal. It would all fit together. But it's important you get the directions correct. Okay, so just as a warning, you've got to be very careful here. So warning, if you had, say, for example, A less than B and then C less than B, this does not, absolutely not, imply that A is less than C. Just as a quick example, you could have 1 is less than 2 and -1 is less than 2, both of them of course, but definitely 1 is not less than -1. So the transitivity, you've got to be very careful, right? You've got to get the direction of the inequalities going in the right way. Okay, so just a numerical example of this to make sure it's completely obvious. I mean, it is very obvious when you think about it. If I take, let's say, a number, I don't know what it is, but let's say it's less than 5. And let's assume, or let's make the observation that 5 is less than 7. That's a true statement. Well, this guarantees what? Well, this absolutely guarantees x is less than 7. It's less than 5, sure, but it is true that it's less than 7. So that's the meaning of inequalities, right? An inequality between two numbers is a relationship between their relative positions on the number line. Now we can use this notation to describe subsets of the number line very precisely. Namely, we can use it to describe intervals. So I'm going to describe the two main types of interval now which we talk about in mathematics, open and closed intervals. And really I want to introduce notation. So interval notation. So this is just going to be a way to describe certain subsets of the number line. So let me just say that. Describe certain subsets. A subset of something is a sub-collection, if you want. So if you take the collection of all the people in the world, a subset of that would be all American people in the world, for example. Okay, so it's the same idea. We have all numbers. Maybe we want to only talk about positive numbers or negative numbers or numbers between two extremes. That's what interval notation is going to do. So when I write down the following, when I write down open bracket, so open parentheses, a comma b, where a and b are numbers. Now this means when I'm thinking about intervals, so this actually will be a little bit confusing. Later on when we're talking about coordinates, this will mean something, but you need to understand kind of what world you're living in. If we're talking about intervals, this notation means the following. So I'm going to use kind of a curly bracket notation to represent a set, a collection of things. This is all x such that x is strictly between a and b. Strictly between these two extremes. So when I'm using this notation, I'm assuming here that a is strictly less than b. Otherwise this wouldn't make sense. You couldn't have a number with this property if a was greater than or equal to b. So I think it's important we have a good way to visualize this. So you should always be thinking about things visually, in my opinion. It's an important skill to have. So we'll take our number line. We'll take our number line. So what have we got? We've got my A and we've got my B. So let's do this kind of in a fancy way. So I'm going to represent the fact that it's all numbers between these 2 points. So A is here and B is here. And at the endpoints, I'm leaving kind of an open circle. And that's to represent the fact that I am not containing the endpoints. See, A and B are not in this because you've got to be strictly between A and B. Now, anything of this form is called an open interval. An open interval. Now, the opposite extreme of this would be a closed interval. And a closed interval, we use bracket notation, square brackets. So it's kind of curly brackets. I don't know, it's not really curly brackets, it's curved brackets for the open. And if I write this instead, so it's very similar, but you've got these kind of square brackets. This is equal to, well, it's going to be exactly the same. So I'm just going to copy it basically. With one key difference, it's also going to include the endpoints. So I'm going to write it like that. And if I was to write that in visual notation using this number line, it would be the same, except now what I'm going to do is fill in the endpoints. Fill in the endpoints. So this is a standard convention in mathematics. Where we have, if something's not included, we have a hollow dot, and if something is included, we make it solid. Now at the same time, we can blend these two. There's no reason not to. So for example, if I had almost exactly the same thing, so maybe I should just say this is called a closed interval. So we could do basically the same thing, but let's imagine doing it one side with a curved bracket and the other side with a square bracket. What should that mean? Well, that should mean you are strictly greater than A, but you are less than or equal to B. That would be logical, wouldn't it, if we're going to fit with this notation? So let's get rid of that. Woo, too much. So if I'm going to do that as a picture, it's going to look like the first guy Nice. It's going to be a hollow dot at A, but it's now going to be a solid dot at B, like that. Cool. So it's also worth thinking about subsets which are not finite. So when I say finite here, I mean they've got kind of a biggest and a smallest value, an A and a B. Or they're bounded above, if you want, or bounded below by some values. It's very useful to talk about things like, well, all positive numbers. And if I talk about all positive numbers, those are numbers that are strictly greater than 0, but there's no upper bound. So it's nice to have notation to deal with that. And to do that, we introduce a symbol which causes a lot of problems for a lot of people because it's purely a symbol, right? It's not a number that I'm going to write down. So if I'm going to talk about something like the positive numbers, I would use this notation. So I'm going to mix and match a bit with my open or closed intervals. So this guy, let's have a square bracket on this side. So I'm going to write A, comma, now I'm going to write the infinity symbol, which is this kind of 8 on its side. And I'm going to write an open bracket there. So when I write this down, this is notation for x such that, well, the only condition is x is greater than or equal to a, or a is less than or equal to x. There's no need to have any condition on the other side. You don't need to say it's strictly less than infinity. The reason you don't need to do that is because infinity isn't really a number, right? This is just a symbol to allow us to kind of unite the idea of this kind of open closed intervals at the top with the idea of only having a bound on one side. So infinity is not a number. This is just notation. So this is the infinity symbol. It's not a number. So let me go off on an extremely short tangent just to explain to you why we don't dare call infinity a number. If infinity was a number, we should be able to do arithmetic with it, shouldn't we? Okay, so let me show you why we don't want infinity as a number. So this is going to be super dodgy, and I'm going to remove it after a second, but I just want to write it down quickly just to illustrate something. So if infinity is a number, what would infinity plus 1 equal, for example? Well, if infinity plus 1, surely that's infinitely big anyway. I don't know, so let's call this infinity. Okay, so that seems logical. If there is any arithmetic you can do with infinity, that should be the case. But now, if we want to keep my properties of algebra, what would this have to imply? Well, this would have to imply that 1 is equal to infinity minus infinity. But now, any number take away itself would have to be 0. Dun, 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 dun. So this is very bad, isn't it? So when you're talking about infinity or using the infinity symbol, it just is a placeholder for something which is unbounded. You're not thinking about it as a specific number. You certainly can't do arithmetic with it or anything like that. If you try to use it as a number, you run into these terrible problems where if the laws of arithmetic hold, or the laws of algebra that we studied at the very start of the course, you run into all sorts of awful problems. So this is kind of very, very, very bad. This is like terrible, terrible. So infinity is not a number. This is extremely wrong. If infinity was a number and we keep our laws of algebra, then 1 is equal to 0, which is clearly crazy. So the choice we make is, okay, I don't want to lose my laws of algebra. We just decree infinity is not a number. Doesn't make sense. So here, it's a bit of a tangent, but it's worth pointing out. So what does this mean? Well, how would I represent this on the number line? Well, it's quite simple. It would be same basic story as above, dot, 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 dot. And I would have a red line now like this, but it would go on forever in the positive direction. And I've decided, haven't I, that it's going to be a solid dot here because I chose a square bracket. So this is your A over here. Neat. We could do it in the opposite direction. just to mix things up, I'll do it with a curly bracket or a curved bracket. So something like this. Notice I'm using a curly or curved bracket here and a curved bracket here because I don't want to have a square bracket, because that would be like saying less than or equal to infinity, and that just wouldn't make any sense at all. So this is equal to what? This is equal to all x such that, well, we're just saying x is going to be strictly less than b. You see I've used a curved bracket here, so that means I shouldn't include the b. So if I do that, what does it look like? Same story, number line. So here, what's it going to look like? I should get exactly the same, shouldn't I? So dot, dot, dot in this direction. Negative infinity, because we're thinking about going in the negative direction as far as we want. And then I don't want to include b, so let's make it a hollow dot b there. And finally, I suppose we could talk about interval notation for the entire number line. If we do that, we could write the following. Minus infinity to infinity. Right? It's kind of crazy notation. All that is just all real numbers. We sometimes write that as script r. That's kind of the proper mathematical way of writing real numbers, so decimals. So this is all real numbers. And if I was to do this, well, let's just cut straight to the chase. It would be everything. The whole thing in both directions. Neat. So this is interval notation. It's a way to describe certain subsets of the number line succinctly. So let's just recap what we've done. The concept of an inequality is a way of describing the relative positions of two numbers on the number line. So we say that a is strictly less than b. Let's go back up here. We say that a is strictly less than b if a is to the left of b on the number line. We say that b is strictly greater than a if b is to the right of a on the number line. So it's always this orientation. So two ways, here, here, and here, to describe exactly the same thing, the same picture. Got to be a bit careful with negatives. It can confuse you a bit, but it's all about their relative position. We can now include this symbol, which would also give us the potential for equality. The moment I have this, we introduce the terminology of positive and negative numbers, of course. Being to the right, of 0 makes you positive. Being to the left of 0 makes you negative. We have this rather important transitivity property, where if you have two inequalities in the correct direction, that guarantees a new inequality. And finally, using inequalities, we can describe very precisely important subsets of the number line.